Hello everyone, my name is Israel Silva Jr. and I'll be presenting on optimizing dioxomolybdenum catalyst for the conversion of biomass to chemicals. Timothy Su is the student that worked on this project before me. Dr. Alex John is my mentor, and I'll be presenting this on behalf of the Chemistry and Biochemistry Department for the Kellogg Honors College Capstone project. Introduction. Petroleum is currently the source of olefins. Olefins are a type of hydrocarbons that are used in our everyday life for gasoline and other fuels. And the problem with this is that fossil fuel resources are the #1 cause of pollution, and petroleum products are non-renewable, meaning we can't use them again once we've used them. So researchers have switched to sustainable resources, for example, biomass-derived resources, that may one day supplement and replace the fossil fuel industry. Chemists have turned to the deoxydehydration reaction, abbreviated DODH, which is a single-step process that reduces our biomass-derived molecules into our alkenes, our olefins that we're interested in creating more of, instead of using fossil fuels. So this reaction uses the biomass-derived molecule here, reacting it with a reductant with a metal catalyst denoted by LMOO2. In our case, we use molybdenum as our metal. In solvent, to create our alkenes, our oxidized reductant add water as our byproducts, but we're mainly interested in this alkene. So advances in this deoxydehydration reaction has been done by Dr. Nicholas. So Dr. Nicholas has used vanadium to carry out these reactions, and they have found very good alkene yields. As you can see here, they got up to 95% yields in their system. But the problem with this is that vanadium and other metals used are precious metals, and we're trying to reduce the cost on using this reaction. The strategy that my research group and I used was to synthesize and explore the reactivity of molybdenum catalysts to catalyze a DODH reaction. Molybdenum was used as a cheaper alternative to vanadium. Change solvents to understand optimal DODH conditions. We start our investigation by doing the ligand synthesis. So we go ahead and react 2-T-butyl-4-methylphenol with benzolamine and 37% formaldehyde in methanol and water at 50 degrees Celsius to create our ligand. And once we have our ligand, we go ahead and react that with molybdenum ACAC to create our complex, as shown here. And what we do to confirm that we've made our products is use NMR spectroscopy, as shown here in this diagram. So now that we've created our molybdenum catalyst, we can go ahead and do the oxidation reactions. We go ahead and start off with styrene glycol, and we put it in this DODH system to create styrene. And the significance of this study is that we changed the catalyst design, and we did a survey on these 4 catalysts. So what we did is we changed this arm that hangs off the catalyst here, and we started with catalyst 1B over here. Catalyst 1B has a very bulky pyridyl group, and we only got a 5% DODH yield. So we went ahead and created catalyst 2B with this amine group, and we got a very slight increase in our DODH yield, but it wasn't very significant. And we think that this was 5% because of the binding capabilities between the pyridyl group and the molybdenum. We believe that that binding is inhibiting DODH activity. To confirm this, we went ahead and created catalyst 3B. The significance about catalyst 3B is that the oxygen is highly electronegative, meaning it's going to hold on to those electrons. It's not going to want to bind to the molybdenum as much. And as a result, we actually got a 31% yield for our DODH. And we were very happy with these results because it confirmed our suspicions. And to finally end this study, we created catalyst 4B. And this is a phenyl group that's not binding at all with the molybdenum. And we found very similar results to catalyst 3B. Once we've optimized our catalyst, we wanted to see how solvents affect the DODH system. So what we did is we submitted a variety of solvents to the DODH like we did with the catalyst, but we only used one catalyst this time, catalyst 4B. And a general trend that we found was that the more nonpolar the solvent was, the better the DODH yield. So toluene, xylene, and mesylene are very similar in their structures, and we found very similar yields. They're around the same range. But when we got more polar in our solvents going down, we found that DODH yield was inhibited, and with water, we found no reaction. Researchers have proposed a DODH mechanism that contains two pathways, pathways A and B. Pathway A suggests that a glycol condensation occurs before the metal glycolate is reduced by a reductant, while pathway B suggests that a reduction occurs before the glycol condensation to yield the metal glycolate intermediate. Though these are two different pathways, they both end up with the alkene extrusion, meaning they both create the alkene that we desire. Conclusion: the nature of the pendant arm in the complex affects DODH capabilities. The reaction is dependent upon the polarity of the solvent. Some of the future directions I would like this project to go in is to explore microwave irradiation methods and create a new catalyst design to see how that affects the DODH system. Acknowledgements I would like to make is to Cal Poly Pomona and the Chemistry and Biochemistry Department, the National Science Foundation for funding my project, and my research group members for helping me through it all. Thank you.